To do assignment 114, you'll need a graphing calculator. This is a challenging assignment, so it's enrichment. You don't need to know how to do this. The initial setup talks about a sample of hydrogen gas in a syringe. So here's a picture right here. Hydrogen gas in a syringe. You should know this Boyle's law here. P times V is a constant value. Now we're assuming that the gas in the syringe is compressed at a rate of 0.200 atmospheres per minute. So imagine the plunger getting pushed in so that the pressure increases at a constant rate, 0.2 atmospheres per minute. So this data table is all about that. You can see the pressure goes up every 5 minutes. It goes up by 0.2 atmospheres, so it is predictable on into infinity. The volume is also predictable because P times V is a constant. So originally it's 1 atmosphere times 24 liters. The product is 24. Now it's 1.2 times 20 also equals 24. 1.4 times 17.1, 24. Try the next ones on your own. In other words, this one right here and this one right here. Pause the tape and come back when you have an answer. Here I got the answer of 15.0 liters, and that's 24 divided by 1.6 atmospheres. This is the pressure volume product. And on the last one, it's trivial. I get 12.0 liters. It is half of the original volume because the pressure is doubled. Now, what you want to do here is think generally. At any time t, what would the volume be? And I'm hoping that you can do this. The pressure will be the original 1 atmosphere plus 0.2 T. At any time t, just add up additional pressure, 0.2 atmospheres per minute, which would mean the volume at any given time t is 24 divided by 1 plus 0.2 T. The density is easy to calculate here. It's 2 grams in the syringe. 2 grams in the syringe are inside there. And so it's just divide that by the volume. So for example, this one is 2 grams divided by 17.1 liters, and that's my density. And so this is trivial. So I get 0.117 grams per liter for this one. And for the last one, 2 grams divided by 12 liters is 0.167 grams per liter. So you can see the density is increasing as we increase the pressure. Density increases, and it's predictable. There is an equation. That's what we're looking for here in the next step. Find an equation that expresses density at given time t. So I've kind of given you a hint there about what it could look like. This is the equation for volume versus time. What's the equation for density versus time? Pause the tape, come back when you have a guess or just to see an answer. Okay, density is mass over volume, which could be expressed as mass times 1 over volume. Mass is 2.00 grams, constant. It's right there. It's a mole of H2. Volume we've expressed in this way, so I need to take the reciprocal of, right? It's 1 over volume, so it's the reciprocal of. So I do this, 1 plus 0.2 T, that's the pressure at any given time, over 24, that was the pressure volume product. So pressure divided by pressure volume product is 1 over volume. So the 2 cancels with the 24, and I just get 1 plus 0.2 T over 12. This is an equation that gives you the density at any time t. I'm going to plot the first function, which I've got which is parentheses 1 plus 0.2. I'm using x in place of t, and divide that total by 12. So this will get me a linear function. The window parameters are here, and this will get you a nice line on the graph, one that you can actually see the slope. Now we're ready to look at the second part of this problem and look at the sample of air. Original density is provided, is warmed in an expandable container. Keep in mind we're looking at the time at which the densities of the gas samples will be equal. Here's the data table for the warmed gas. Starts at 20 degrees C, rises 5 degrees per minute. Here's your picture. Volume is proportional to Kelvin temperature. So if I can get the Kelvin temperature pattern, I'll know the volume will be proportional. So for example, this first one here is, if I look at what is the volume at 413 Kelvin, all I have to do is take this ratio of 413 Kelvin to 293 Kelvin. Volume at 293 Kelvin was 1 liter, so this is it. That's all I need to do. And my calculator tells me that the answer is 1.41 liters. And the density is simply take the mass of gas, which is constant. 1.21 grams of gas is in my original 1 liter sample. So I'll now have 1.21 grams over 1.41 liters. And it says, leave this as an unsolved expression. You can calculate it. But for the purpose of this question, it'll be better if we just leave it as a function. See if you can get the next two volumes here. See if you can find the pattern. We are looking for an equation that expresses the volume at any time t. Here you can see my numbers for these t equals 48 and t equals 96 minutes. And now I'm ready to look for this equation. At any time t, the temperature, you can see, always starts with this 293 is constant. That was my initial value. And then this is 5t. 5t plus 293 equals the temperature at any given time t. The volume, since it's a ratio, will therefore be 5t plus 293 is the current temperature over the original temperature, 293. That's the volume at any given time t. The density is the mass over volume. So that's a little tricky. But we have this equation. The volume at any given time t is 5t plus 293 over the original 293 Kelvin. The density is mass over volume. So once again, I'll use the trick of saying density is mass times 1 over volume. And then I can take this volume here and flip it upside down. So the mass you've seen is the constant 1.21 grams. That's the constant. And the 1 over volume, the reciprocal of volume, will be 293 over 5t plus 293. And so that could be, that's a function right there. That is a function. If you wanted to simplify the top, it's possible to do so. 1.21 times 293 is 355. And the bottom is 5t plus 293. I'm ready to type in the second function, which from my paper is 355 divided by quantity 5t, but I'm using x, plus 293. And now that gets me a curve. This is not a linear function. This is a curve. So if I look at the graph, there's the linear function I plotted earlier. Here's the curve for the density of the warmed gas. It starts high density and gets lower as time progresses. But you can see there is an intersection. If I calculate the point of that intersection, then I will have found the answer to my question: at what time do they have an equal density? So I'm hoping you know how to do this. And here are my coordinates of the intersection. The x value is time, the y value is the density at that time. And I have checked these values in my equations to verify that the density of the heated air at this time will be equal to the density of the compressed hydrogen at that time.